With Lee Coy. My name is John Stella, and I'm in the Department of Forest and Natural Resources Management at SUNY ESF. This is Lee's, the culmination of a very long and wonderful journey of hers. I'm just going to introduce Lee a little bit, and then she'll do her presentation. Lee was born in Guangxi, China, in the very southern province, the most southern province of China, and came to us at ESF with a wealth of experience. She got her bachelor's degree in chemical engineering at Southwest University of Nationalities. She got 2 master's degrees, one at Sichuan University and one at Texas A&M. Before that, though, she was she was an executive director of a NGO in China, the Green Students Organization Society, where she worked on projects such as global warming, invasive species, aquatic pollution, and was there for 6 years and then continues to consult and is on their board. She's very comfortable in front of the camera, as you can see, and has from there went and did a master's at Sichuan University looking at invasive species in urban settings. She was also an environmental educator. She has written several books for middle schoolers on environmental issues. From there, she started her U.S. journey at Texas A&M, where she worked with Georgianne Moore, studying the ecohydraulics of an invasive weed called Arundodonax, which is a big problem in southwestern riparian zones. Before coming to ESF, she did a stint at the Earth Corps in Seattle, where she did things like plantings in riparian zones, invasive species eradication. She met lots of friends there and filled in. And this is this sort of typifies her tremendous spirit that she brings to all of her interactions and her work. Lee is the most positive, efficient, and really motivated person that I know. From there, she came to ESF, and immediately I bundled her off onto on an NSF-funded project to the St. Anthony Falls Stream Lab, St. Anthony Falls Lab in Minneapolis, in the middle of the Mississippi River, where she conducted an experiment that you'll hear more about. She worked in an outdoor sinuous flume, and here she is planting cottonwood and tamarisk seedlings in the middle of a flume. She also did a stint with one of her committee members, Pat Shafroff, at the USGS Fort Collins Science Center in 2012, where she did air photo interpretation and GIS analysis. Again, you'll hear more about this. That was related to the Bill Williams River, a sandbed river in Arizona. And then she went back to a flume, but this time at UC Berkeley, where she did other plant experiments that you'll hear about in 2013. After that, she has been on the Elwha River, again with Pat Shafroff, and has done quite a bit of traveling since you've been here.
Oh yes, many states.
She's also begun to publish her chapters. Last year she published a study in water resources research on one chapter. She has another one. We just found out she's invited to resubmit it after revisions, and 2 others are well underway in the works. So she's quite launched, and I just have to say, in her interpersonal skills, Lee has been a tremendous lab member and leader here at ESF. So I just want to appreciate you, Lee. And let's get on with the science. How about?
Good.
Okay.
Good. Thank you for the long introduction. Very helpful. Cheer me up. after all the social part, we get into the science part. So today my dissertation is the reciprocal interactions between fluvial processes and riparian vegetation. And they're at different scales. Well, don't be scared by the title. Too many big words. I know that sounds big. So let's skip the title and just look at the image. So are you fascinated by this amazing looking shape of a river? I took that picture 3 years ago in Arizona. And when I step in the middle of the river, it's like, oh, wow, this is amazing. Okay, now the science question pops up. This is amazing. So are you curious how the water shape like this, how the river shape as it is? And are you curious how the plan was performed at the side of the bank? So that's the two big components here, and that's all my research is about. It's the rivers and the plants. So when we get to these two big components of the river and plants, they have so many interactions. They never independent of each other. So all the existing rivers that you saw here, well, they will do something on the other one. For example, what do I mean here by these two terms? Okay, there are so many things that happen in the river. The fluvial process means many things. I want to point out two major things, which is my focus on the study. It's the hydrology and sediment that are inside the river. So hydrology is a flow, it's a water that transported in the river channel. And the sediment also, it's when the water transported, naturally carry the sediment with it. So it's the sediment and water that in the river. That's what I mean about fluvial process. And that's how the river was shaped initially. And then at the vegetation part, what do I mean here? It's the species and densities. Well, when we talk about vegetation dynamics, there can be so many things. And what I mean here, it's focus of my study. It's particularly on the species, so variety of species, biodiversity along the river, and also the density. It's a dense or sparse or it's bare surface on the river. So that's what I mean. So what's the interaction actually happening here? So many interaction. I point out that something kind of at a broad scale of my study is the first sea dispersal. So when a flood coming through a river, some hydrochorid species, they tend to have a sea at the time when the flood comes, and the flood carry the sea and disperse downstream. That's a way that how the floods interact with the plants. And also, some plants, for example, like cottonwood, they tend to require floods as a manner of recruitment. So when flood comes, they wet the area, and the seed will able to germinate as a piece of the bare surface. So some plants require floods to recruit, and also some plants was able to handle the long-term inundation of the flood. So those kind of plants tend to grow close to the river. So all this is a few important things that are happening in terms of how the flood affect vegetation. But on the other way, so this is a feedback interaction process. It had to have something happen on the other way. So on the other way, when vegetation starts to grow on the sandbar, and it grows those roots, and then the roots was able to hold on the soil. So it can actually stabilize the bank. And so when the flood comes, it wasn't able to scour the soil as fast as it can if there's no plant growing there. So bank stabilization is how the plants provide for the fluvial process. And then also channel migration. So if anywhere that has a plant, floods may take longer to scour that piece of land, and then channel may be migrating slower. So that's how the interaction happening in the riparian corridor. And so that's all the interaction going on. And then what I want to focus on here, in my study, it's the flood and the plant and the physical disturbance of the flood. So flood can inundate the plant, but that's the physiology part of the plant. I want to focus particularly on the physical part. This is the least study area that in the riparian ecology is how the flood can affect the plants. So when we talk about flood affect the plants, there are two things here. One is a scour on top of the image, And then the other one is the burial. So when flood coming through, it can scour the substrate and then uproot the plants. Or when the flood coming through, it carry a whole bunch of sediment down on top of the plants and potentially bury the plant. So plants can die because it gets scour, uproots. Or plant can die because it get completely buried under the soil, not able to photosynthesis and growth. This is small scale. So we look at very narrow, small scale. That's how we look at the plant and river interaction. How about the larger scale? So we talked about that before. All those species, and they grow closer to the river. They are able to handle long-term inundation. They are able to handle the physical disturbance of the flood. That's why they tend to grow close to the river. And then some plants grow further away from the river. They potentially, they may prefer drought instead of being inundated in the river. So plant distribution along the river, from the longitudinal standpoint or from the lateral standpoint, they are controlled or driven by the flood frequency and magnitude. So this is from large scale. And how about on the other way? So we talk about that, okay, how the fluvial process affects plants. So how the plant affects fluvial process from a micro scale is, okay, we look at here. It was potentially, there was a bare sandbar here, and then an army team of the tammers start to invade in this sandbar and grow on top. And you can see the plants start to stabilize this sandbar. Okay, when the flood comes, here you zoom in the camera, look at the very detail here. So when the flood comes through, some area that right close to the tammers, it actually has a higher deposition. And somewhere slightly further away from tammers or between the plants, it actually has a scour happening here. So that means when we look at the micro scale, the plants stabilize the soil, slow down the water velocity at where the plant is. And anywhere there are no plants, because it's scoured. So that's how the plant change fluvial process at the micro scale. And the larger scale, okay, we're going back to that graph. When that plant start to encroach, that's another term, plant encroachment along the river. When plant encroach along the sandbar, and it stabilize that sandbar, and then every time when there's a deposit here, the plants get onto the sandbar. So the river kind of tend to go narrow and narrow over time because there's a plant able to stabilize that piece of the land. So that's from larger scale, you can see that the river geomorphology change. For example, channel width change and channel sinuosity change, which we're gonna get to that term later, what those terms actually mean. And all this scale, all this interaction happen naturally without human. But human intervention have been greatly affect this from changing hydrology and sediment. This is one case here. So on top, there's before a dam was built, there's a free-flowing water. And then they have a sediment equilibrium condition. I want to introduce this term just because I need to use that later. So in the sediment equilibrium condition, there's a balance between the transport capacity of the water and the sediment. So overall, if you look at the channel river corridor scale, there's no drastic deposition or scour happening in that region. And okay, you see this is a dam. So after building a dam, when flood coming through, this dam trap all the sediment behind the dam. And then at the downstream, you don't see that high peak flow going through. And then, so hydrology change. So peak flow change, the magnitude of the flood change, the frequency of the flood change become decreased. And on the other hand, there's a sediment deficit condition downstream of the dam. What that means is most of the sediment get trapped behind the dam and not passing through the dam, most of the sediment. And so problem happen here is downstream the sediment become coarser and then channel become incised just because there's no sediment supply from the dam. So that's an issue for the flow regulation and dam construction. And that, what to do with the plants and river morphology downstream? That's one of the management questions. How this flow regulation can change the downstream biodiversity and can change the downstream geomorphology. And so there's another thing happened in the southwestern region of the US. So we look at these red spots. Those red spots on the graph, that's where the cottonwood willow is supposed to be dominant in this region. And this region, so cotton and willow, they were dominant species in the southwestern semi-arid region of the river. And they provide a great habitat for the wildlife in that region. They have been existing there for a long period of time, and now something happened. So there's an invasive species called tamaris. Okay, invasive species, they come in quickly, they expand faster, and in that region. And problem come out and people trying to control that plants because they just grow too fast. They occupy all the space that's supposed to belong to cotton and willow. So cotton and willow start to decline in that region, and these invasive species start to expand. So of course, people spend $1 million trying to control that thing. So what happened? Okay, people suggest because the cotton and willow require flood to recruit or to resprout. So in order to have that, in order to come back to that natural flow, and then people start to doing a flow release on a regulated river. So the river was damaged, and then people want to come back to the natural flow. So what do is they release the flood at the time when cottonwood and willows start to germinate or start to release their seed. And then so we want to mimic that natural flood regime and to help the cottonwood and willow to come back to their natural status, to come back to have more and more cottonwood and willow grow along the river. But now the question comes out here, is if you release the flood for promoting the tamaris and to promote the cottonwood and willow in that region, can you also use that flood to get rid of the tamaris? So this is one of the flood release experiment that on one of the rivers. So you can see before we release, that's what you see. There's an island in the middle of the channel, and after a flood, some plants get scoured and washed away, and some plants still stay in that place. So another question is, if we want to get rid of tamaris, can we just use a flood control, and then we release large enough flood and just wash out that tamaris? Then we don't need a herbicide control, then we don't need the mechanical way to control that. So it's a way of people thinking. That is also one of the big management questions that support this dissertation, is whether flood control is a useful tool. So just keep that in mind. We're going to answer it in the last slide. Okay, so we have this scientific need for doing this research, and we have this management demands to support this research. And we trying to understand these interactions between rivers and vegetation. I break that down into 3 questions here. So first 2 questions, so look at a plant from a smaller scale. So how easy a plant get killed by the flood. And then second question is how the plants affect the fluvial process, means affect the sediment deposition pattern in the river. So that's from small scale. When you zoom in your camera, you look at the individual plant on the sandbar. That's what it is. And then on a larger scale, so over longer time, riparian vegetation and river, they co-develop together at the same time. And how this co-development trajectory happening in a heavily altered river, which means the river have been heavily flow regulated. And then how this can potentially affect the vegetation and the river that below the dam. So, and my focus is particularly on the Sandbag River and in the semi-arid region, which towards southwestern part of the US. And then my focus also on the species, focus on the tamaris, cottonwood, and willow, because they are the dominant, right now they are all the dominant species in the south and western region. So I want to know how those plants are doing there and trying to come up with some sort of prediction for future management needs. And I try to fit all my study into a scale So y-axis is a temporal scale, so moving from seconds to decades. And x-axis is a spatial scale and the square meter scale sense. So it can be a fluvial bar, so maybe from couple meters to 100 meters. And the largest scale is like river corridor. It's 10 of million square meters of area that I'm trying to research. And then from the plant standpoint, it can be from individual plants on that sandbar, or it can be a vegetation community that across the entire river corridor. And so I have a full experiment. First, I want to say the first two they focus on the individual plants that are on the sandbar. And these are two flume studies that they simulate the different kind of sediment conditions, sediment and flow condition. And I'm gonna combine them together. They all belong to what I call it small scale study. So you can zoom in camera to look at those very closely about sediment deposition pattern and plant mortality at the individual scale. And this is the largest scale study. It's a long-term study over 45 kilometers of a river. And it's over past 60 years of the study from the history area photo analysis. And there's one study here I'm not going to talk about in any sort of detail here, but just give you a one-sentence conclusion here is, this is a study I'm trying to do to validate all the assumptions that I did for all this previous 2-week study. So the one conclusion is, the tamarinds and cottonwood, if they get completely buried, they will die. So that's the one conclusion. Just carry that over for the experiment. And just a short note here. So 2 of these papers, it's this is already published. This is getting close to publish in the revised major revision stage. And those 2 are very close. Hopefully I can get it done in 1 month. Very ambitious plan, very productive PhD life. Okay, so we get into small scale, the plants in the patch. So we're talking about small scales. First, if we want to talk about interaction, we have to know whether the plant looks different or not, because the plant's morphology, they contribute different sediment deposition pattern in the flow, right? So first, before we do all kind of interaction study, construct model, we want to know how different they are morphologically and plant trait. And then second, we want to know how the floods kill a plant. That's an easy word. But break that down into sediment burial. So any kind of plant that get completely buried means the sediments over top of the plant height. The plant will die from the third experiment. That's a very classic conclusion from that experiment. And then the other one is dislodgement. So when the flood coming through and wipe out all the substrates, the plants were uprooted and then get washed downstream. And we believe they are dying at the downstream. So this is how flood affect plant. And on the other hand, how plants affect the deposition pattern. That's also what we want to know to document this interaction process. So what do? Okay, we spend a month in Arizona and trying to collect all those small seedlings on the sandbar, both tamarinds and cottonwood seedlings. They were naturally growing along the river, and we pull them out, and then we pack them, ship them to the experimental station, and then we put them in the pots at the different density. One is sparse, which have only 2 plants. The other one has 10 plants in the pot, so dense ones. I'm gonna mention that later. And then 3 months later, they look like this. Very awesome. So far, because they've grown very good, so my experiment have been going very smoothly. Very lucky. And then, so we want to do the plant structure analysis. First, we want to measure the plant trait. For all the riparian ecology or somebody doing plants, you like to measure the height, the root length, and stem flexibility, and a few other parameters that for each of the plants. And second, very importantly, the plants are doing very different thing when they are in the water. So we measure a parameter called frontal area distribution of the plant, which means when the water coming through a plant, it doesn't see all the way of the plant. You only see when it hits the plant. You see the area of the plant that's perpendicular to the water. So that's where the water see the plants. So what we do, we want to mimic how the water see the plants, and we will pull that plant out of the pots, and then we were able to wash out all the soils without destroy their roots, orientation, the location, and then we put them on the blue board, and then we photograph them. Then we use software to extract all the pixels of the plant, and then just calculate the area of the pixels to know something we call it frontal area. It's how the water see the plants and when water coming through a plant. So imagine if a plant has a bigger leaf, it tends to have a larger frontal area, and it tends to slow down more of the water and cause sediment deposition. So that's the logic behind this. And then so we have a straight flume channel. Both are man-made channels, so they are not real. Both channels are man-made. This one is in Berkeley, this one is in Minneapolis. I do that at a different time. And this straight channel is to mimic the sediment deficit condition, which is the rivers that has dam on the upstream. So they have a limit amount of sediment supply in that channel. And then the other one is meandering channel. This is meandering channel in Minneapolis. It used to simulate the river condition that at the sediment equilibrium condition, where it means we have a constant sediment supply from the upstream for this section of the channel. And then just give you a heads up, that's supposed to be the result, but give you a heads up. In any kind of sediment deficit condition, plant dislodgement are mostly likely to happen. So when there's no sediment, you have a flood keep coming through it, you're gonna wash out all your substrates and plant dislodge. And when there's a sediment equilibrium condition, plants are more likely to be buried because you have sufficient sediment coming from the upstream and then deposit on the plant and bury it. So give you a heads up how this can potentially affect the plant mortality. And then what we do, so we have this sediment in the flume, and we have a naturally developed sandbar that on the meandering channel before we do this. And then so we need to excavate all the soils in the flume and in the channel, and then try to mimic the same area of where the sandbars are. And then we insert all the pots that in the channel, and then we construct the pots in a special way that we can separate the side of the pot and the bottom of the pot. So what we do is we cut the bottom and then we reconnect it with a zip tie. So when we lower the pots in the flume, we cut the zip tie and we can take the side out without disturb the soil and the roots and the soil. So we remove the pot sides, which this guy is doing. He just lifts in the sides, and then the soil and the plants and roots still stay in place. So that's a good good simulation of a plant encroachment on the sandbar. And then we release the water and sediment in the flume. We are able to control them very well. And then we measure the surface elevation before the flood and after flood, and want to know the differences of the sediment deposition pattern along the plant. We measure it in a centimeter scale, so they are very fine. And then we determine plant status. So in the straight flume, which is sediment deficit condition, we recover the plant from downstream net. Those are the plants get dislodged. We are able to know where they're coming from, where did they get dislodged. And in this bottom graph, we dig out all the plants. We know which plant get buried in the sediment. So plants die in two ways: get completely buried, and then all get scoured downstream. So you don't have to remember this graph. I'm going to show that again. Just want to show you the configuration of each flood. So we have a 9 floods here. And then each flood has a different species, either cottonwood or tamarisk or mixed. We have a plant size, either short or tall, small or tall plants, or mixed. Or we have a different density, either sparse or dense plants. So because we believe that the plant size and density matters when the plants that sit in the flume or experience a flood. So this is the result. Those plants looks very different. And these are cottonwoods. They single stem, throughout leaf on top. Those are tamarinds. They are like a shrubby plant. So you see a whole bunch of stems coming out from the bottom. And how the stat shows. So tamarinds, they are red, and then cottonwood are green dot lines. You can see that the y-axis is the location of plants, and then x-axis is the frontal area. So the pictures, the pixels that we took. So we do analysis and say, oh, so tamarinds compared to the cottonwood, tamarinds has a lower crown, and tamarinds has larger crowns, larger frontal area as well, with the same height when these two species are the same height. That's what tamarinds doing. And tamarinds also have more roots and the below ground part. So what that tell you? If a flood carry the sediment travel through these plants, tamarinds is more likely to slow down the water velocity because it has a larger frontal area. It's more likely to cause sediment deposition around the plants because it has lower crown and it's a larger crown. And here, if those two plants in a sediment deficit condition, where means a scour happening, anywhere that has tamarins can potentially has less scour because this plant has massive roots and they are able to hold the soil. So with the same stream force that going through these two plants, tamarins tend to holding the soil very well and survive the scour condition. So remember this story, and then we're gonna go to here to explain why this is happening. There's so many numbers, and only thing I want to tell you is that the last column percentage. So this is a percentage of mortality for all these runs. And then what they can tell us is, first, plant size matters in terms of how the plant died. So when we compare cottonwood, short ones and tall ones, and tamarinds, short ones and tall ones, all the small plants tend to have a high mortality because they are small. So when the flood coming through, even with only 10 centimeters of scour, it's able to uproot the plant and wash it downstream. So that plant is dying. So when it's small, but when it's big, it has more root system established, so it can stay there longer for longer scour. And then the other one, species matters. Because the morphology differences between these species, it actually triggers very different mortality at different conditions. So on top is the cottonwood and the dislodgement condition. So in the deficit condition, we have 64% of cottonwood get washed downstream, they're gone, they die. And then for the tamarinds, it's 39%. So in any kind of condition that can cause plant burial, tamarinds is more likely to die. So going back to flow release, well, whether that plant die or not, it depends on the condition of that river, depends on hydrology and sediment condition of that river, whether that create a potential burial condition or that cause a scour condition for that plant to die. And different plants die at a different time. And so species matters. And then density also matters. So when we compare sparse patch and dense patch, we can see that cottonwood has only about half of the mortality compared to the sparse one. So what that means, when plants grow very densely and they're holding their roots together, the roots tangle together, and they are able to secure the soil, stabilize the soil, so they are less likely to get dislodged. So plant would be good if they will grow in the very dense patch. That's how the simple interpretation are. So that's the story how the flood affect the plant mortality. And then this is the story how the plants affect the sediment deposition pattern. It's okay, we see top two graph. This is sediment differences measured before the flood and after the flood. The red one means they have a big deposition in the patch. The blue one means they have a scour. So we can compare the top two graphs here. compare cottonwood and tamarinds at the same condition, tamarinds tend to trigger or induce more of the deposition. So when I get to this point, I was like, oh God, that tamarinds, basically they introduce a lot of deposition around that plant and potentially bury themselves. And that's how they die. That's just a simple cartoon version of the story, but that's what is happening in the river. It's tamarinds, if they are in the burial condition, meet the hydrology and sediment transport, these all the conditions, and they can bury themselves just because they have larger frontal area. And then the dense patch compared to the bottom two graphs, so the mixed dense patch tend to have a higher deposition compared to the sparse patch. So when there are lots of plant there, it's naturally trigger more of the deposition in that region. So what's a brief summary of these two studies? Larger plants has a decreased vulnerability of the flood. So when the flood gets larger, it's not gonna get buried because the stand is high. So even you have a 10 centimeter of sediment travel through it, it's not gonna able to bury that plant. So a lot of plants have more time to grow. You can survive the burial. And compared to the cottonwood, tamarinds has larger frontal area, which causes sediment deposition and which causes its own mortality in the river. And the other hand, when the tamarinds, because tamarinds is a greater root mass, and then it was able to stabilize the soil. So in any kind of sediment deficit condition, it's less likely to get scoured and washed downstream. So it's safe in this condition. So size matters, plant species matters, and all these species and density that we talked about, sparse and dense one, it influence the sediment deposition pattern. So this is the two experiment that document this feedback and interaction in a scientific way. We thought that in the many field observational study, and this is the one that actually document the feedback, one of the first ones. Okay, and so we talk about a small scale. Now we get to a larger scale. How this larger scale can potentially, how the interaction happening on that larger scale. So I do a research on this long-term river evolution, use of area photo analysis. We have this 45 kilometer long river that's called Bill Williams River, and they are on the west part of Arizona. They are part of the Colorado River. And here's what it looks like. That's the river. So river, we have many cottonwood grow right along the river. And we have those dense tamarinds patch slightly further away. And then this river was dammed in 1968. So after the river was dammed, so we're curious how the river geomorphology changed over time. We're curious how the plants develop over time. And there must have some sort of interaction going on. So I had two research questions for this large scale study. First, how the plant develop on these high and low flood plains. So we in the river formation, in the landform, we have some low flood plains and high flood plains, and how those plants develop over time in the condition of the regulated river. And then on the other hand, how the channel width, braiding, and sinuosity responds to this expansion of these tamarinds, or the change, the shifting of the community. So what those terms mean? Channel width, how wide the rivers are, and braiding is the branch of the river. So if a river has more branch, we tend to call it as a higher braiding. And then the sinuosity is the curvature of the river. So the meandering river has a higher sinuosity compared to the straight channel. So just some definition of the terms. So what do we do here? We have two layers on the same area image and thing. If you happen to do software analysis called GIS, you'll know that we use different kind of layers on the GIS. The top two are the vegetation layers. So vegetation has three cover types, including cottonwood willow as a group, or tamarisk, or other vegetation, such as mesquite. That because we're more interested in those two, so we group others in the other plants category. And each of the plant category has a dense, can be either dense or sparse, depends on the percentage cover on the ground for each of the polygons. And then so we can see here in 1953, this area was a bare surface. And when you get to 2009, one corner become dense tamarisk, one corner become dense cottonwood. That's how we delineate the vegetation cover along the river. And then for the bottom one, this is geomorphic analysis, which include the low and high floodplains. So we can see that in 1953, this is the 1953 high floodplain. But as the river moving over year, by the time you get to 2009, we have this 1964 low floodplain, which means in 1964, it was a flow channel. So we call it low floodplain. And then we have the 1996 high floodplain. That means in the year of 1996 area photo, it was a floodplain. It wasn't a channel. It was a floodplain. We can see that they have a record of inundation at one period of time. So high floodplain here means it never become a channel. It never been a channel, but it was inundated occasionally by the flood. Low floodplain means it was a channel at one point. So we have these two delineations, and then we intercept each other, and then get to this point is zoom out a little bit. We have all these floodplains that was formed at different years. So as the river migrates through it, it creates a new floodplain. And we have this colorful map here that demonstrate, okay, 1953 was all this area, 1953 never been changed. And then as you go that, okay, this is 1964, the river was like that. So we are able to distinguish each of pixel, each of area when it was formed. If you are in the stats, here's the equation. So in order to answer the question, we construct that model, but don't be scared by the model. What I want to say here is, I want to tell the cottonwood and tamarisk percentage change over time on different kind of floodplain. So basically, I want to know how the vegetation developed on the different floodplain with different vegetation type. And the other side of the story, I want to know, since tamarisk expand a lot, we know that from aerial photo, you can see that from 1953 to 2009, a lot of tamarisk occupy that area. So we want to know how those percentage change of the tamarisk and cottonwood potentially affect that three river geomorphic indices. Sorry. Okay. And then so how the channel width, gradient index, and sinuosity change associated with the percentage cover change of the river. This is the overall story. So I'll just show you that this vertical bar is the peak flood. So we can see that before the dam, we have many big floods. But after the dam, because of flow regulation, we never see those giant big peak over there. So both flood magnitude and frequency decrease significantly because of that dam. And then on the other hand, the vegetation. So vegetation grow rapidly from 1970 and 2010. So with that, about 40 years of differences, we got vegetation grow about 4 times on the river. So how vegetation grow 4 times, that total area, how the tamarisk and cottonwood doing differently. So I break that into 4-panel graph with different species and different floodplain type. So just some big story here is on the high floodplain, which means the floodplain was inundated occasionally by the flood. Tamarisk grow rapidly here. And then cottonwood actually had a slightly decrease. Okay, I think that's what we see on the high floodplain. How about on the low floodplain? Oh, surprisingly, that we got that cotton will grow, or cotton will still increase, with the tamarind a slightly decrease. What that means is, well, when we say that, oh, cotton will have been replaced by the tamarind, and tamarind expansion a lot. That's the general invasion plant science on the river corridor. But this research contribute to a more detailed level is, yes, the tamarind increase, it more likely to increase in the higher floodplain. And then on the low floodplain, where the abandoned channels are, the cotton is still able to remain its dominancy, and it coexists with the tamarind. So tamarind is not able to compete very well with cottonwood in the low floodplain. That translates into a management strategy is, if you are able to release a flood large enough to create channel migration, you create those low floodplain in that region, or abandoned channel in that region, you are able to increase the cottonwood in that river corridor. So that's one of the implications. So we have to tell another side of the story, how the vegetation affect the channel. As we see, vegetation increased, and then at the same time we saw channel narrow by 70%. It's a lot, like from 50 meters something down to 1. And then we saw sinuosity slightly increase from 1 to about 1.1, very small increase, not too big deal. And then this is channel braiding, which means the channel has less and less branch in this region. And then this is stats results. All these change occur strongly, significantly in the area that dominated by tamarind. So tamarinds grow in that region. For some reason, it actually caused the channel geomorphology change more significantly. So imagine when we do a small analysis, micro scale analysis, we saw tamarind has a huge effect on the sediment deposition pattern. And here, tamarind has a huge effect on geomorphology of the river as well. So this is take-home message here. So a short summary of this long-term study is, if you have a free-flowing water river before it was dammed, and then when you build a dam, let's say 1 to 5 years after you build a dam, because the flood magnitude decrease, and then the sediment transport decrease, supply decrease, you have more of the exposed bar here. And then at this stage, vegetation starts to grow because there's no flood disturbing it. And then at the same time, you have a sinuosity, doesn't change that much because you just have an exposed bar. And then braiding index actually increase just because the exposed bar increase. You just see more branches because it has those bars exposed. And then this is the stage that human modified hydrology that caused us drive significantly about the river shape and vegetation change. How about after 10 years of that? So we see that after 10 years of dam closure, vegetation actually become more significant drivers on the river after 10 years when vegetation starts to establish here. So we saw dense patch of vegetation grow right along the river where they have a better access to the water. And then we can see channel width significantly decrease, and channel is more confined and deeper at that point. And then we can see the braiding index start to decrease because all of the bars occupy the plants, and then the channel gets shifted and then only confined in a certain region. So channel become simpler. So just one spread channel, not multiple branches. And then all these affect that tamarinds contribute more significantly here. So that's a short conclusion for this part. So we have done research on both the small scale and large scales. And here is my conclusion here. Interaction exists on the river. We document the interaction in both the small scale and the larger scale way. And I make some small cartoon version to understand and as a take-home message. So we have this single stem plant, cottonwood. we have these shrubby plants. And how the flood affects these plants? As the flood can dislodge that plant easily, and flood, if in an equilibrium condition, in a bendfold flood condition, it can bury these tamars easily, shrubby plants easily. How the plant affect the sediment? Yeah, every plant can increase the sediment deposition, but tamar can trigger more of the deposition along the river, contribute more to the sediment deposit on the sandbar. And how those plants contribute to geomorphology change of the river. So in the area that dominated by the cottonwood, it still maintains about natural flow looking river, so have some exposed bars and then slightly wider channels. So anywhere with the tamars occupied regions, it tends to have a more narrower and sinuous and less braiding river. So river become more simplified in this region with tamars dominance. And then when the river morphology change, vegetation community change as well. So on the low flow plains, and you see we have a cottonwood and tamars co-dominant, with cottonwood still able to maintain its maximum at the low flow plain. On the high flow plains, we have more and more tamars grow in that region. I think one of the reasons because tamars was able to handle the drought condition better than the cottonwood. So those are the short, simple stories here. So back to our management question. It's, can we use environmental flow to actually wipe out that plant, wipe out invasive species? Yeah, that's possible, yeah, but there are many uncertainties. So if we want to, we're looking at these two graphs. The y-axis is the percentage of dislodgement and percentage of burial for the small plants and tall plants. And we use the 20 centimeter as a cutoff. So this is just a magic number we pick. So we are looking for somewhere that more tamars die, which is here. So we have to create some sort of sediment equilibrium condition and then to bury the plants. And then we may get about 30% of more tamars dying in those conditions. So translate on the river is, if there's a free-flowing water and a free-flowing river, and when the flood coming through, we may expect that there's more of the mortality happening on tamars patch because they get buried by the sediment. But on the other hand, here, if we are able to allow the cottonwood to grow taller and then release the flood at this point, we are able to get tamars dislodged. So that translates into real field. Give you an example. So cottonwood tend to germinate sometime late March, early April. So if we are able to leave that cottonwood to grow to the end of the summer, when it past 20 centimeters, but the end of the summer, for example, August, a group of tamars start to germinate. And then so if we release the water somewhere in August or in September, the tamars is still here, cottonwood is here. We are able to expect there's more mortality happen on tamars. So it's possible, but many things happen because all I mentioned is there's an interaction going on the river. And the hydrology and sediment, they perform completely different at different sections of the river. So this contribute to the big uncertainty on the rivers. If you release a flood, how you actually control at each micro scale or each sandbar, how those sediments and hydrology conditions match what we need. We're not sure. We cannot realistically do that. But so this contribute some uncertainty on the research. So one sentence is, yeah, it's possible, but use it with cautious. Okay, all the study I described, and I really want to thank you, my advisor, John Steller. He has been spent tremendous time on correcting my Chinese version of paper writing. and he spent a lot of time on that. I really appreciate that. And also, he's perfect advice on securing the funding. I've been living here very well, so I'm happy with that. And also other committee members give me feedbacks on the paper, and I have many collaborators. This is an NSF funding project. We have 3 universities here. We collaborate pretty much every year on the film studies and on other part analysis on paper publication. So I appreciate all kind of collaboration that here. And also thanks friends, whoever show up here, and friends connect on the other side of the internet to listen to my presentation. So, thank you. So we have
a few minutes for questions.
Few minutes. Maybe take a couple questions. Yes.
So you're not talking about trying to replicate natural systems, because there would never be a flood in August in the Southwest.
In the Southwest, not likely gonna be have a flood. That's not natural. It's like man controlling. If we want to release at that time, it would be more like we control the flood. It's not natural.
So, and also the likelihood that any water agency would choose to release water in August seems pretty small.
Yes, so that's the big thing. We was original plan to have some sort of flood release because lack of water over the past 4 years. So we are not able to release the flood from an actual river. So this provide a methodology there. But if linking back to reality, there are so many agencies, they want to keep the water in the reservoir. They want to make sure people can learn to boat there. So there are issues on the negotiation of whether that become real. Yeah.
What about monsoons?
Monsoons?
Arizona monsoon.
Arizona monsoon, that happened, yes. In terms of precipitation region, yes, they are in the monsoon region. They have rainfall sometimes. But since climate change, the fact is over the past like 4 or 5 years, it doesn't really happen. So for the fact of Southwest, it doesn't really happen. But it was in that monsoon region in terms of precipitation.
But there are, the natural system in the Southwest does have a bimodal precipitation, right? It has winter precipitation and some snow melt in high elevation. But it also has monsoonal floods that do scour out the channel under natural conditions. So it's not usually part of the flood release because it's a small amount of water, but it's but it can scour out the channel, right?
Yeah, hopefully.
Under historical conditions.
Yes. Yeah.
I have a question for you.
Yes.
So I always have an issue with the idea of invasive species, because I know in Europe we worry a lot less about invasive species because we've had hordes of barbarian crossing Europe for thousands of years, and it's really a survival of the fittest over there. So I was wondering, when you look at the tamarix, you say it's invasive, I get it, it wasn't there before, and we have that idea that there is an ideal state where there was cottonwood and willows, we don't want to change it, it was beautiful. And then in terms of ecosystem services, what does the tamarix do that is bad? Why? Because there are some invasive species that we need to get rid of, so I agree. They have truly huge negative impact on the system. Because the tamarix, aside from changing the species diversity, is it bad in terms of ecosystem services? Is it destroying, I don't know, what is it doing? Why should we put so much energy into removing that plant?
Okay, good
Aside from
question.
the idea that it's invasive, I get it.
Yes. So when I was in Texas, and my advisor was actually doing this study, why the tamarisk was banned. So from her perspective, so one of the arguments she has is because it's taking more waters, so it consumes more waters. So in the semi-arid region, water was supposed to be a resource that we want to conserve. But because that plant grows a lot on the river, it takes more waters than the cottonwood and willow. So river's flow level become less and less. One of the reasons that because that it consumes water. And the other ones that I read some of the literature, it said some birds that they like to nest on the cottonwood willow. And now this is species coming, and that bird doesn't like to nest in that pointy, that leaf. So they affect the bird. But in terms of ecosystem services, well, that's the wildlife part. This ecosystem services, our water is the most concern in that region. Yeah. Yeah. We get to the time now.
Questions? Okay, well, let's thank Lee.
Thank you for coming.
Great. Take some refreshments on the way out, and we'll reconvene in just a few seconds to